When you hear the word acid, what's the first thing that pops into your head? For a lot of us, it's probably a bubbling beaker in a science lab, right? Something dangerous. But what if I told you that you run into acids and even eat them pretty much every single day? Let's get into it.
Okay, I know, this sounds like the beginning of a really weird riddle. You've got a sour fruit, a staple in your kitchen pantry, and then a heavy-duty household cleaner. They seem like they're from completely different worlds, but they all share one fundamental chemical secret.
And there it is, the secret's out. They all contain acids. The vinegar you use for salad dressing? That's acetic acid. Lemons are packed with citric acid. Grapes have tartaric acid. Apples have malic acid. And hey, even the sting from an ant? That's formic acid. They are, quite literally, all around us.
And this makes perfect sense, doesn't it? The name itself gives us a huge clue. It comes from the Latin word acidus, which simply means sour. So that sour tang you get from lemons or tart grapes, that's the acid talking. So we know they're in a lot of things, and they can taste sour. But let's put on our chemist hats for a second. What actually, on a chemical level, makes something an acid? It's time to uncover that core definition.
All right, here's the formal scientific definition. Now, it might look a little intimidating with all the symbols, but I want you to focus on that last part, the hydronium ion. That is the calling card, the absolute signature of every single acid when it's in water.
Let's break this process down. It's really all about what happens when an acid takes a dip in some water. The very first thing it does is let go of a hydrogen ion, which is really just a single proton. We write it down as H+.
Now this little H+ ion is super reactive. It's way too unstable to just float around by itself. It's got to find a partner, and fast. And since it's surrounded by water, the most obvious choice is a water molecule, H2O.
And here we go. This is the final step. That lonely H+ ion latches onto a water molecule, and together they become H3O+, the hydronium ion. This is the true signature of an acid. If you see this ion being formed, you know for sure you're dealing with an acid.
So now that we know what an acid is, let's take a look at its big, diverse family. Because just like any family, you've got different branches and all sorts of different personalities.
First up, we can sort them by where they come from. You've got your organic acids, which come from living things, plants and animals. They always contain carbon and are usually pretty mild enough to eat. On the flip side, you have inorganic or mineral acids. These are made from minerals. They don't have carbon, and they tend to be much stronger and more corrosive.
We can also group them by strength. And this isn't just about how dangerous they are. It's about how completely they break apart or dissociate when they're in water. A strong acid goes all in. It breaks apart completely, creating a really high concentration of those hydronium ions. A weak acid is a little more hesitant. It only partially breaks apart, so you end up with a mix of some ions and some whole molecules just floating around.
And one last way to categorize them is just by looking at what they're made of. This one's pretty simple. If the acid's formula has oxygen in it, like sulfuric acid, we call it an oxyacid. If it's got hydrogen and some other nonmetal but, and this is the key part, no oxygen, like hydrochloric acid, then it's a hydracid.
So we've met the whole family, but where do they actually come from? Well, let's open up the chemist's cookbook and take a peek at a few of the top recipes for making acids.
There are a few key ways to do it. First, you can use synthesis, which is just what it sounds like, directly combining hydrogen with a nonmetal, like chlorine, to get hydrochloric acid. Simple. Second, there's the action of water. You can dissolve a nonmetallic oxide, like carbon dioxide, in water. This is actually how you get carbonic acid, the stuff that makes your soda fizzy. And third, you can use oxidation, where you take a powerful chemical to force oxygen onto a nonmetal, like turning sulfur into sulfuric acid.
Every chemical has its own unique personality, a set of properties that tells you how it looks, feels, and reacts with the world. So let's get to know the personality traits of acids.
Physically, we've already covered that they have a sour taste. But I'm going to say this again. Please do not taste chemicals in a lab. The strong mineral acids are incredibly corrosive and can cause very serious burns. Because they form all those ions in water, their solutions are great at conducting electricity. And of course, there's the classic party trip. They change the color of chemical indicators, like turning blue litmus paper red.
So that's what they look and feel like. But how do they act? How do they behave when they meet other chemicals? This is where we get into their chemical properties.
One of their signature moves is reacting with active metals. Think zinc or magnesium. When an acid comes into contact with one of these metals, you get a reaction that produces two things: a chemical salt and a stream of hydrogen gas bubbles. It's a classic acid reaction.
And maybe their most important reaction of all is with their chemical opposites, bases. When an acid and a base get together, they neutralize each other. They basically cancel each other out. And what are you left with? Just a salt and plain old water. This is one of the most fundamental ideas in all of chemistry.
Phew. Okay, we've covered a ton of ground, from the lemon in your kitchen to the chemical reactions happening in a lab. So let's boil it all down to the most important points to remember.
So, what do you need to remember? Number 1, the real sign of an acid is that hydronium ion, H3O+, that it makes in water. 2, acids are a huge diverse family. They can be organic or mineral, strong or weak. 3, they have a very distinct personality. They're sour, can be corrosive, and they react with metals and bases. And finally, just remember that from our food to our factories, acids are absolutely essential to our world.
And that leaves us with one final thought. An acid can be strong enough to dissolve metal, yet it's also gentle enough to be in the apple you eat for lunch. This stuff is literally essential for life. So what does this incredible duality tell us? To me, it shows just how critical context and concentration really are, not just in chemistry, but in pretty much everything. It's something to think about.